Good morning. My name is Haoyu. As Xiaodao just introduced, I'm a first-year PhD student in his group. And first of all, I want to say a big thank you to this workshop for giving me this opportunity to introduce my work. So this is part of my first project on the North American craton imaging. And today I will mainly introduce you some preliminary results on the crustal thickness and this Rayleigh phase velocity below the North American midcontinent. So the North American craton is one of the oldest continental cores on the Earth, which has been existing for billions of years. And on the contrary to what people previously thought, that the North American craton has a relatively simple and stable interior due to its longevity, it turns out it has quite complex tectonic features. As shown on this map here, where our study area is enclosed by this black box. And we can see multiple basins, such as the Michigan Basin, the Illinois Basin, and the Forest City Basin. We can see there are also several domes, such as the Ozark Dome and the Nashville Dome. And also there's the Midcontinent Rift, and also several arches marked by those blue lines. So since the tectonic features are manifestations of the tectonic events that a certain area has experienced, it looks like the North American craton has a complex tectonic history. And this figure, studied from Wang et al. 2023, shows parts of the tectonic events that the North American craton has experienced since the Proterozoic. So from left to the right, the North American craton first experienced the separation of the Rodinia supercontinent from around 0.8 to 0.6 billion years ago. And at the same time, the formation of the Great Unconformity from about 1.25 billion years ago to about 500 million years ago. And later and both the separation of the Rodinia supercontinent and the formation of the Great Unconformity are considered as uplifting events to the North American craton. And at around early 300 million years ago, it experienced the formation of the Pangea supercontinent, which is a subsiding event to the North American craton. And later, at around 200 million years ago, it was the separation of the Pangea supercontinent and the formation of the Atlantic Ocean, which were both uplifting events to the North American craton. So all of these uplifting and subsiding events together formed the complex tectonic feature we can observe today. So since variations in the lithosphere structures carry information about the tectonic history, we would like to explore reversely to see how is the crust modified by those tectonic events. And to answer this question, we mainly use two approaches. The first one is synthesizing published crustal thickness model and LV depth models to extract the shared features across models to have a more robust and clear observation of the spatial variations. Then the second analysis is to construct a crustal anisotropy model to study the crustal layering, especially within the crust. And at this stage, we obtained only the phase velocity maps. And in the first analysis, we collected a total of 9 mobile depth models and 3 LV depth models from the ARIS EMC dataset. Since all the different models have different emphasis, they have different distinct features, but we focus only on the shared ones. And here are some examples of the models we use. The top 2 are the mobile depth models. One is local, one is global. And the bottom 2 are the global LV depth models. And we can see that they have different coverages and different resolutions. So in order to make them comparable, we need first to resample them to the same grid size. And in this study, we use 0.1 degree by 0.1 degree. Then the second step is simply averaging our models to emphasize the shared parts and to remove as much as possible the not shared ones. So our synthesized Moho depth models reveals Moho depths in the North American craton varies from about 35 kilometers to 355 kilometers. And under the basins, we can see that the Illinois basin has a relatively deeper Moho depth comparing to the Forest City Basin and the Michigan Basin. And whereas when it comes to move to the west part of this map, the Moho depth just generally increases to about 50 kilometers. And for the synthesized LAB depth models, we can see that in the North American craton, the LAB depth is generally varies from 190 kilometers to about 250 kilometers. And under the Michigan Basin and the Illinois Basin, we have a relatively shallower LAB comparing to the Forest City Basin, which is quite deep, like around 250 kilometers at least. Whereas for the other part of the North American craton, the average LB depth is around 200 kilometers. And when it moves to the west part, where it's about to the Rocky Mountains, the LB is quite shallow, like around 100 kilometers or even shallower. So beside the Moho depth and the LB depth, we also calculated the mantle root thickness by simply subtracting those two like previous models. And our model shows that, again, in the Illinois and the Michigan Basin, they have a relatively thinner mantle root comparing especially to the Forest City Basin. And also these two basins are surrounded by some thick crustal roots. And it is the interesting observation, like it implies some horizontal modifications under these two basins. And we would like to find how these horizontal modifications are formed. And besides all of this, the full waveform ambient noise tomography results by Yang et al. I would like to show some figures here, but it hasn't been published. So due to confidentiality, I can only describe the observations. So from the ambient noise tomography results, we can observe two strong low velocity zones under the Illinois Basin and the Michigan Basin. And we assume, and we think that they might be high radio anisotropy layers. And all of these previous different models combined with this low velocity layer motivated us to study the radio anisotropy under the North American craton. And it moves to our second analysis. So in the second analysis, we use CCF, ambient noise CCFs to retrieve the radio wave phase velocities and the log wave phase velocity in the future. The CCF is cross-correlation functions. And at this stage, we collect the data from 872 seismic stations, both the permanent US array stations and some more dense temporal, like regional seismic arrays. And the data we use are from January 2011 to December 2013. And at this stage, we use only the vertical component to calculate the radio wave phase velocity. And in the future, we'll use the horizontal components to calculate their log wave phase velocities. And the sampling frequency is at 5 Hertz. And this figure just shows you some quality control of our results. And those are the move-off plots at different stations at different frequency bands. And we can see clear the radio wave arrivals from 5 to 50 second periods. And it kind of, I think it's a pretty clear arrival, and it looks like our data quality is quite good. And to calculate the cross-correlation functions, we use the periods centered at 5, 8, 15, 20, 30, and 40 seconds. And then we applied the frequency domain random mean average. Then lastly, we calculate this cross-correlation using a 12-hour chunk with 6-hour overlap. And in the future, we'll extend the periods to up to 100 seconds to explore the deeper structures. And it is just an example of the dispersion curves we obtained using a Python package called AF10. And after getting the group velocities, we use another Python package called FMST to calculate the phase velocities. So in order to optimize the reliability of our results, we filtered out the empirical Green's functions that have signal to noise ratio smaller than 5. And also we removed station pairs that are closer than 4 times of the minimum period of interest, which is 5 seconds in our study. And this dispersion curve shows quite beautiful dispersed features at higher periods. So again, our work is quite robust. And here are just more data, not data, just more like validation of our results. Here we compared the shear wave velocity at 13 kilometers with the phase velocity perturbation at 8 seconds. And we can see both show the low velocity perturbations in the noise basin and Michigan basin, as well as under the mid-continental rift. And we can see the similar high velocity perturbations at these regions and near the Ozark domes. So again, it validates our results. And here are just some preliminary results on the phase velocity perturbation. And the left one is at 15 seconds, the right one is at 20 seconds. And there's a low velocity perturbation under the Michigan basin at 15 seconds, as well as in the Wisconsin, whereas at 20 seconds, the low velocity perturbation just disappeared. Then at higher periods, at 30 seconds and 40 seconds, we see that both the positive and negative perturbations emphasized in all locations. And at 40 seconds, the low velocity perturbations at Michigan basin and the mid-Wisconsin just appears again. And there's one more feature we need to focus to notice that under the mid-continental rift and some parts of the Tennessee, the low velocity perturbation just extends all the way from 15 seconds to 40 seconds. So it means it is probably just cut through the crust. And that's all the results I have for now. And in the future, we will obtain the log wave phase velocity to calculate the Rayleigh anisotropy, and we will extend our periods to 100 seconds. And after that, we'll combine with multiple other seismic imaging techniques to have a more comprehensive understanding of the North American crater evolution. And at last, we are planning to have a model to describe all these observations. Yeah, that's everything.
We have time for questions.